Hello, calculus students. So we are going to be doing one of my favorite topics today, and that is finding volumes of solids using known cross sections. So here's a basic idea. Suppose that I have the x-way plane is flat on my hand, and I'm making a solid out of this shape. So I have on my base on the x-way plane, I have two curves. And the area between those curves is forming the base of my solid. So you found the area between two curves in the last lesson. So now what we're going to do, we're going to take some shape, use that as the base, and we're going to have the shapes come up off of the XY plane and form a solid. So let's say I'm using rectangles. So here's a rectangle, and I put that there. Now that doesn't look like much of a volume. So I'm going to get some more. Here's another one, and I keep adding rectangles. In fact, I'm going to add infinitely many rectangles until they fill all the space between the two curves, forming a solid. And the reason why we call this volume by known cross sections is that your cross sections are some shape like a rectangle or a triangle or a semicircle. All right, so we're going to start today by reviewing some formulas, some area formulas. I'm going to share my screen and start the presentation. All right. And so first we're going to talk about the review of some area formulas. So most of you know, let's see, area square. Let me grab my pen here. Hopefully my pen will show up. There we go. Let's go back, grab my pen. And let's say we're talking about, say, a square. So here's my square. Oop, I got to go back a slide. I forgot we're doing the area formulas. There we go. So let's look at, this is not my day. All right, we're going to look at a square. All right, and if that square has side lengths that are x units long, then the area of the square would be equal to x squared. All right, so we also are going to look at the area of an isosceles triangle today. And I'm going to do it a little different way. So I'm going to take that square we had. Notice I made it a little bigger. And if I cut it at its diagonals, you can see I get 4 triangles in here. Each of these triangles is an isosceles right triangle. All right, the base of that triangle is x. And most of you know that if your hypotenuse in an isosceles right triangle is x, then each of these sides is x divided by the square root of 2. All right, so that's kind of a long way to get there. So we're going to look at the area of this triangle another way. So if you notice, this square is made up of 4 such triangles. And if we know the area of the square is x squared, then the area of the isosceles triangle is going to be equal to 1/4 of x squared. And that's going to be really useful in some of the problems that we're going to be doing today. Another problem you may have seen before is, let's say we have an equilateral triangle. Right? Remember, equilateral, all sides are the same. That means all the angles are 60 degrees. And maybe when you first learned how to find the area of an equilateral triangle, you drew the altitude down here, made this little right triangle. And now this is a 30, 60, 90 triangle. And if my side lengths are x, that means that this little side length here is x divided by square root of 2. And the altitude or the height of that would be x divided by 2 times the square root of 3. And so the area would be equal to 1/2 the base. Now remember, when we're talking about the base, we're talking about the entire equilateral triangle. So we'd have 1/2 the base times the height, which we just said is x divided by 2 times the square root of 3. So 1/2 base times height. So putting that all together, I'd get that the area of an equilateral triangle is, let's see, we have a 1/2 here, and this is also a 1/2. So a 1/2 times a 1/2 is a 1/4. We have an x here and another x, so that's x squared. And then we have our square root of 3. So the area of an equilateral triangle is 1/4 times the side length squared times the square root of 3. So those are some useful ones. We're also going to see semicircles today. Area of a semicircle, you probably know, is pi times the radius squared divided by 2. All right, so let's take a look at some of our problems. So the first one says, find the volume of a solid whose base is the region between y equals x squared and y equals 4, and whose cross sections are isosceles right triangles with the hypotenuse on the base. So remember, that's the example we just talked about in that previous slide, where we have an isosceles right triangle, right? And we have the hypotenuse here. So this is one of these where we can say, oh, the area of that is 1/4 of whatever the side, right? Whatever this side length is squared, okay? That was the shortcut way to find the area of an isosceles right triangle. All right, so I'm going to draw a sketch of our problem. Remember, the area between these two curves is what's making up the base of the solid, and so these solids are coming up off the page. So first I have x squared. I don't know why we're so crooked here. And then we have y equals 4. So I'll just say that's at 4. And so this is the base of our solid, and then our shapes are coming up off of that. So I'm going to switch colors here a second. And these are isosceles right triangles. So this side length here, right, that's in this shape here. So I have all these isosceles right triangles with the hypotenuse on the base coming up off of that. So you kind of have to picture these are coming up, right? Those are sticking up. So again, this length here of this side, right, this representative rectangle is the same as this. All right. So that means that the area of one of these triangles is 1/4 times the side length. Well, the side length is this piece here, which in terms of our figure is the difference between these two curves. That's what we did last class. So remember, it's the top one minus the bottom one, and our bottom one is that x squared. All right, so it's 1/4 times the difference between those two curves squared, right? So this is taking the place of this x, this whole piece here. So 1/4 the side length. So if you picture it, if you drew a square out here, right, this is 1/4 of one of those squares. And so we have that. Now, that's just one triangle. And in calculus, in order to get infinitely many of those, we turn this into an integral. And our integral is going from this point to this point, and we're filling that area between these curves with infinitely many isosceles right triangles with the hypotenuse on the base. So infinitely many are in between there. So I need to know these limits of integration. In other words, I need to know, where does x squared equal 4, right? Those are both my values. And you probably already know that our x is going to be equal to plus or minus 2. So those are my limits of integration. All right, you may also have noticed, well, first of all, and I'm going to switch colors here. You may also have noticed this has a constant, so I can take that outside. I'm also going to put my dx in there, which I should have had. Remember, that represents the representative rectangle width, right, is delta x wide, or dx. I'm going to pull my 1/4 out in front because it's a constant. Remember, we can take constants outside of an integral, but not a function of x or a function of y. So now I'm down to this. And something else I can do to make this problem a little easier is I should notice that this is in fact an even function. So rather than going from -2 to 2, I can double this. So I can multiply it by 2 and make this lower limit of integration start at 0. So in other words, I'm just doing the right side and then doubling that. So 2 times 1/4 is 1/2. So I have 1/2 times the integral of 0 to positive 2. And to simplify this part inside the integral, I'm going to go ahead. Notice I can't I'd be saying to myself, oh, was the chain rule done correctly? No, there should be a negative 2x in here, but I can't invent a function, right? I can't throw a function in and take its opposite out. So I need to just FOIL this. So 4 squared is 16. I have 4 times negative x squared and 4 times negative x squared for a total of 8 times x squared, negative 8 times x squared. And x squared squared would be a positive x to the 4th power. So that's what I get when I square this whole thing and do that times dx. All right, so I'm going to find my antiderivatives. I have everything I need here. I'm going to keep the 1/2 outside. Antiderivative of 16 is 16x. Antiderivative of 8x squared is 8/3 x cubed. And the antiderivative of x to the 4th is 1/5 x to the 5th. And I'm evaluating that from 0 to 2. And this is why we like to use that doubling factor when we have an even function, is that 0 is so much easier to work with, right, than that negative 2. All right, so I'm going to go ahead and evaluate. I put in 2. I get 16 times 2 is 32. 2 cubed is 8 times 8 is 64 thirds. And here I have 2 to the 5th is 32 fifths. And then I simplify all of that and I get, oh, and I could have put my -0. Notice I skipped that step, right? This is -0 in here somewhere. Should I have that? Right, if that helps you. Right, we evaluated at 0. And so I end up with my final answer. I'll do that real quick. Grab the old calculator. Don't forget you have to multiply by that 1/2 at the end. Sorry, wait for my calculator to warm up here. And we get it's loading. Guess I should have turned this on sooner. All right, so we are going to do 32. I could have found my notes and gotten here faster. I don't know why it's so slow. Okay, 32 minus 64 thirds plus 32 fifths. So I do that. And I get 256 fifteenths. That's this part. So I have 1/2 times 256 fifteenths. And then 2 goes into 256 128 times. So I have 128 fifteenths. All right, so let's look at another slide here. This time, same problem, but this time my question is, find the volume whose base is the region between those same two curves, but this time my cross sections are semicircles with the diameter on the base. So I'm going to grab my pen. All right, so we still have our same parabola. We have our same, here, I'll put my beautiful axis here, 2, 3, 4. All right, so again, this is our shape, this is the base, but this time we have semicircles coming up off the base, right? We have infinitely many of those coming up to form a solid. It'd be like some, look like, I don't know, little dome like a snowball, half a snowball shape or something. All right, so now we still have our integral. Our integral is still going from -2 to 2, right? But now if I look at my representative rectangle here. My representative rectangle is the diameter here, right? That's how tall that is. So the diameter is the difference between the two curves. So my diameter is 4 minus x squared. So that means the area of one semicircle, right? One of these semicircles has an area that's equal to pi times the radius squared divided by 2. Well, if my diameter is 4 minus x squared, my radius is going to be half of that, or 4 minus x squared divided by 2. All right, so when I put it into the area formula, I'm going to have pi times, and actually I'm going to bring this 1/2 out front so it's a little easier, 1/2 of pi times my radius, which is 4 minus x squared, divided by 2. All right, so there's my pi, my 1/2. Here's my 1/2 out here. Here's my pi. My radius was half the diameter. And then we're going to square that. All right, so when I put this in the integral, I would like it simplified a little bit more. So this is 1/2. When I square this 2 that's inside, that's like I'm squaring another 1/2. Well, 1/2 squared is 1/4 times this 1/2 is 1/8. I still have my pi. And now all that's left inside there is 4 minus x squared. Now, I'm going to put that into my integral. I have my 1/8, my pi, my 4 minus x squared dx. Okay, again, the dx is this representative rectangle. That's how wide it is, right? It's delta x wide. So now if I look, I can take out the 1/8 and the pi, right? Those are both constants. I'm going to switch colors here. So I'm going to take out 1/8 pi. I'm going to put my integral back. I'm going from -2 to 2. 4 minus x squared dx. And again, remember, this is an even function. So I can change my limits of integration, go from 0 to 2, and multiply this outside by 2. So if I change this to 0 and multiply by 2, I now have on the outside 1/4 pi, or pi over 4, times the integral from 0 to 2 of 4 minus x squared So we've already done this work, right? This is what we had in the last problem. We had this 4 minus x squared. When we found the antiderivative of that, we ended up with, that was 16, so 16x minus 8/3 x cubed. And you can look back at your notes. And then we had 1/5. X to the 5th was the antiderivative of x to the 4th. And again, we're evaluating that from 0 to 2. And so when we did all of that work, oops, did I lose my x here? Yeah. When we did all that, we ended up with our 32 minus 64/3 plus 32/3, or 32/5. So the only difference between this and our last problem was we multiplied by 1/2 at the end. And in this case, we're going to multiply by pi over 4. So we have pi over 4 times, and I believe it was 256/15 is what we had. All right? So we're going to end up with 256 divided by 4. That must be, let's see, 60. I'm grabbing the calculator, the world's slowest calculator. Hopefully it won't take so long this time. We have 256 divided by 4. I should be able to do that. 64, that was going to be my first guess. So we have 64 15ths pi, okay? And we could do this again with a different shape, but I think you get the idea. So the base is always going to be the area between two curves. And then the height is just going to be whatever cross section they give us, right? That tells us how tall the shape is. All right, so your homework today, it says WebAssign. This is an old assignment. Your assignment really is on AP Classroom. I believe it's homework number 27. I'll verify it if you check on Schoology. I do want to go to that last slide for a second here, because I would like you to see some examples of what these look like if students build models. So if you look, looks like their base on all of these was x squared. This one looks like the shapes are squares. I'm not sure these are maybe rectangles or maybe some sort of triangle. These look like rectangles. This looks like semicircles. So if you build all these together, it does in fact form a solid. All right, good luck. Again, that's not your assignment. Your assignment is really at AP Classroom. I believe it's 27. If you have any questions, you can shoot me an email. Otherwise, ask me in class. Okay, good luck.